Okay, so in this video, we're going to look at the binomial distribution and what it is. We'll do a couple of examples in a different video, but in this one, we're going to look at what the binomial distribution is, why is it useful, and how to distinguish whether you need to use it in a particular situation. So first of all, it's also known as a Bernoulli sequence or Bernoulli distribution. So you might see either of those words, they mean the same thing. Now for a distribution to be called binomial or Bernoulli, the following points must each be true. So when you're going through all of your questions with probability, the way you're going to distinguish it as binomial is by checking, first of all, that it only has two outcomes, which we call those a pass or a fail, or success or failure. It happens or it doesn't. The probability of the success happening every time does not change. It is entirely constant for every single trial. There's nothing about if it happens today, then this is the probability tomorrow, but otherwise this is, no, that's conditional probability. The probability of success must not change every time. Like if I roll a dice a number of times, the probability of getting a 1 on the dice does not change every time. The third one is all trials are independent of previous events. So that rules out any probabilities that are without replacement. So you'll often see with the binomial distribution, they won't tell you to use it, but it will refer to usually things that are with replacement or something that may not be replaced at all, like if I'm rolling a dice, it's just constant, the same thing happens every time. So they must be independent of any previous results. And the final thing that's there, it's not going to be in your textbooks. It's not going to be anywhere specific in terms of a special condition, but really it should be, and that is that specific order is not required. Anything that has a specific order of events is not binomial. If you want to have something, I know, success, success, failure, failure, you do not use the binomial distribution for that. Instead, you would just do a tree diagram in your mind. So here's a couple ideas. The options I mean, so the probability that 2 out of the next 3 coin flips land on heads. Well, it's 2 out of the next 3. That's not order. That means I could get heads, heads, tails, or heads, tails, heads, or tails, heads, heads. There's no specific order. So yes, that is binomial. The next one, probability that for the next 3 flips, we get tails, then heads, then heads. That is a specific order. And because it's a specific order, no, that is not binomial. Now, when we're dealing with binomial, what we do is we define it. Now, we can write the words X is binomially distributed, or we can save ourselves a whole lot of time and write this. And this says that the variable X, remember capital letter represents a variable, is binomially distributed with that mean, a mean of whatever it is. Not mean, sorry, with number of trials of n. Number of trials n, and probability of success being equal to p. So instead of writing out X is binomially distributed with number of trials being n and probability of success being p, we just write X, that squiggly line, bi, np. That's what it means, shorthand. Then if this is true, if X is a binomially distributed variable, then to calculate the probability of something happening, so capital X is the variable, little x is how many times it'll happen. So find the probability of this particular variable happening x times, we use this equation here. So we have ncx, p to the x, q to the n minus x. Now, this thing here and this thing here are alternative ways of writing the same thing. And that is ncr is calculated by this. You've got to remember this from previous years of maths. This could be asked in a tech-free exam, and you have to be able to do that. Remember, n is the total number of trials. X is the number of times success happens, and n minus x is how many times it doesn't happen. So Either you get success or you don't. So if X was 4 and N was 6, that means, oh, I didn't get success twice. These two here must add to give you 6 because I'm doing 6 trials. And if I get success 4 times, that leaves twice I didn't get success, which means it's failure. Now the P in that is the probability of success and the Q is 1 minus P, where P is the probability of success. Again, if you have success, that is one option. The only other option is failure. It's the complement. So 1 minus success will give you failure. Now, if you're using a calculator for more difficult ones, we're going to use the menu, probability, distributions, binomial PDF option. This is for the TI Inspire, of course. And these are your entries: number of trials, probability of success, and the number of things, the number of successes that you want. You don't need to hear about the widget because I haven't given you the widget in this video. We can also calculate anything greater than or equal to just by adding probabilities together. So if I want to find the probability of being greater than or equal to 3, you would add the probability of getting 3 successes, 4 successes, 5 successes, all the way up to the number of trials. If we had 7 trials, it'd be up to probability of X equals 7. It would go up to however many trials we have. If it was just bigger than 3, it'd be the same thing, except you don't include the 3. You would get rid of that one for bigger than 3. A very useful property for us, though, is X being bigger than 0 is the same as 1 minus the probability of 0. Remember, we're going to have all the probabilities are possible, but this one just means I get all failures. All failures. Every other possible chain of events has at least one success. So if you take away all failures from 1, you get the probability of at least 1 success. Again, on the TI, you've got menu, probability, distributions, binomial CDF this time because you're doing a cumulative distribution, you're adding them, and you've got trials, success, lower value, upper value. Now the binomial distribution is not that hard to use, but why do we use it? Now let's get rid of all this. I don't know why this is down here. I forgot to delete it earlier. Why do we use a binomial distribution? Well, let's think about this as a tree diagram, perhaps. Let's do my first trial. This is trial 1. On a first trial, I've got 2 possible options. I can succeed or I can not succeed, which we're calling fail. Now let's say the probability of succeeding is 0.6 and fail is 0.4. If I succeed, then the probability of success again has not changed. It's still 0.6, and therefore I can still have failure at 0.4. And the same thing here. Success, failure, 0.4, 0.6. Now, if I said to you, find the probability of 1 success, that would be this set of branches from a tree diagram and this set of branches added together. So you would do 0.6 times 0.4, and there were 2 of them, so you times it by 2. If I then add another layer on, success, failure, success, failure, and so forth all the way down. Now I've done 3 trials, so trial 1, trial 2, sorry. This is the results from trial 1, trial 2, trial 3. Now if I said to you find the probability of 1 success, you now would have this one, success, failure, failure. And that would give you 0.6 times 0.4 times 0.4. Then I can go failure, success, failure, which again would be 0.4 times 0.6 times 0.4, which again is the same as the previous one because you can change order of multiplication. And then you could get 0.4 times 0.4 times 0.6, which is the same thing. So that's all 0.4 squared times 0.6, and there are 3 of them. Let's continue on. So tree diagram isn't too bad at the moment, but let's continue on. let's go to another level of tree diagram. And I promise I'll stop after this one. You have SF down there, because I don't want to keep drawing this forever. This is going to be boring doing it, to be honest, even though I'm organising this for you guys. All right, now if I say find the probability of getting one success, well, you go success, failure, 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 all the way through. That's going to be 0.6 times 1, 2, 3 of them. So 1, 2, 3. Then I got failure, success, failure, failure. So failure, success, failure, failure. Then I'm going to go failure, failure, success, failure, and failure, 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 success. All right, so each time you're still getting 0.4 cubed times 0.6, but this time there were 4 of these. All right, so what you're finding is once I've done a level of trials, the probability of one individual branch having one success is the same every single time. And we simply count up how many branches there are. Now, the how many branches comes from the NCR thing in the equation of the up the top. This P was the probability of success, and we wanted one success, so 0.6 to the power of 1, P to the power of X. This thing here is the probability of failure, 1 minus P, so 1 minus 0.6 is 0.4. And then this is how many failures we want, which is 3. Notice 3 plus 1 gives you the number of trials, which was 4. So what the binomial theorem does, binomial distribution, sorry, is reduces the need for a tree diagram. Essentially, it's one giant tree diagram in our minds. And instead of making us count through them all to find how many chains are what we want, this value here calculates them all for us in one go. I mean, the example I chose of one success each time is pretty straightforward. But if I start going to things like, I want 2 successes, there's 2 there, 2 failures, and 1, 1, 1, 1, and 1, no, no, yes, and so forth. It gets a lot more complicated, particularly as you increase more. Now, I don't know about you, I don't want to be drawing a tree diagram with 10 trials and 2 options each trial. There's over 1,000 branches by the time you finish there. So the binomial distribution condenses this, makes it much more simple to calculate probabilities of large chains when we have those 4 conditions met. And that's what the binomial distribution is all about.